Okay, so what we did last time was, so we ended with showing, so last time we did that for the uniform spanning tree. There are, so if you take uniform spanning tree rooted on the arc AB, so it will be like a picture like that, something. And you fix C on the other arc from B to A. Then there are two discrete functions which together are analytic. Then F is discrete holomorphic, let's say delta holomorphic, where F is U plus IV times the normalization factor number of uniform spanning trees, so a number of forests of two trees, where U was that probability that point, let's say that it's on the plaquette, so probability is that the face is right of eta, and V was the probability in the double uniform spanning tree that a vertex belongs to the upper tree. And then these two functions, they have boundary values, fairly clear boundary values. So clearly V is equal to 0 here, because if you are here, then you of course belong to the, if you're on the bottom, you belong to the upper tree. Here you have U equals 0 because you can be right of this curve. Here you're always right of this curve, so U is equal 1. What will happen is that if we were to have a holomorphic function F, that would be a map to a half strip. So. And then once one proves this, one can show that our curve converges to an SLE just by sort of looking at this function F at a point Z. It will be martingale with respect to the curve, because when we explore working with the right hand rule this curve, we just keep the same boundary conditions. So we can plug it in, and well, these specific functions will get converged to SLE 8. So the only question is why discrete function with these boundary conditions should converge to the continuous functions with these boundary conditions. This is essentially, so it's as well, I would just quote a theorem. If there will be time today at the end, I will prove it, but the theorem, it's a very old one, so it's current Friedrichs and Hans Levy, 1928, so that this F delta converges uniformly to F, which solves as delta goes to 0. So they have a seminal paper where they study discrete boundary value problems, essentially, well, there are many ways one can do it. For example, if you know this F is holomorphic, if you already know the convergence, then F will be holomorphic. Why? Because this discrete analyticity implies that discrete contour sums are 0. So in the limit, discrete contour integrals will be 0. So F will be analytic. Now the question why there is a convergence, you need some sort of subcompactness, and well, the easiest way, the one they used, there are other ways, is that basically, well, for example, if you have this map, the area of the image, if you chop off the top of the thing, if you chop off this, the area of the image is finite. So the area of the image, it's area integral of f prime squared. But it turns out that the same area sum for f prime squared in the discrete case will be finite just by looking at the properties of the discrete analytic functions we discussed. So it's the Dirichlet norm. So you have a sequence of functions where this Dirichlet norm is bounded, and that's almost enough to have a precompactness. That's enough to have precompactness in Sobolev space, which is just a little bit worse than having continuous convergence. So this is one of the ways to do it. Another way to do it is just to use the properties of uniform spanning tree or loop erased random walk. We know that the branch is the same as loop erased random walk, and that is enough, like people who study random walks, for them it's enough to show that these functions will be uniformly Hölder with the same exponent. For that you just need to show that the probability that a loop erased random walk passes in between 2 points distance epsilon is smaller than some power of epsilon. So it's basically the same, it's like a probability that we know the probabilities that random walk hits something, so it can be estimated through this. So I don't want to do this part, and I don't want to do the calculation. So what I want to do today is to give a self-contained proof that percolation converges to a SLE6, so that was the first time first thing which Schramm tried to prove, and there were two reasons why for him it was obvious that it should be a SLE6. One reason is that he could do some calculations for percolation and they returned the same results as physics conjectures for percolation. And the second thing, it's we didn't do this calculation, but what you can do, you can, for example, if you grow a SLE from this point, and then you grow another curve, a SLE or other curve from another point, you can see what happens if you commute these two processes. First grow the first and then the second, or the other way around. So it will be some small drift. So if you grow 1 and then 2, or you grow 2 and then 1, then there will be a small change in how this curve looks. It will be a sort of tilt left or right. And so for every SLE you can do this calculation, and it turns out that SLE6 is the only one where there will be no tilt at all. So somehow terms with the drift, they cancel out. There is a factor kappa minus 6. So it means that the SLE6 has this property that it really doesn't care what happens away from the place where you grow it. And this is what happens also with percolation. Percolation is a local process. You don't care about the boundary conditions. So let me just, so what I want to prove is that percolation converges to SLE6. We do know this only for one model. So it's, so percolation. So we do side percolation on triangular lattice. So it's the same as plaquettes on hexagonal lattice. So every hexagon is open with probability equal to p, closed with probability equal to 1 minus p. And then we study clusters of open hexagons. So we study clusters of open hexagons. How this looks like? Well, it's difficult to draw a hexagonal lattice, but unfortunately we cannot prove it for the square lattice, so I have to draw the hexagonal lattice instead. So we cover them with two different colors. Let's say open is blue. So tossing coin for every color, and then for every hexagon. And then you ask a question, for example, the standard question which was asked because it originated as a problem in statistical physics of whether a water can seep through some membrane. So whether there is, for example, you can do for some shape where there are 4 points on the boundary, A, B, C, and let's say Z. And you can ask what is the probability for a given P that there is a connection between BC and ZA. So in this case, there is a connection. So there are a couple of observations. So if you have so first observation is that this is increasing in P, because well, the bigger is the P, the more open hexagons you have. So an exercise is to sort of give a rigorous proof of that. So the rigorous proof is done with coupling. You have to couple situation for P and situation for P plus epsilon, and the best way to do it is to have three colors: open, semi-open, and closed. Open with probability P, semi-open with probability epsilon, and closed the rest. And then show that if you add semi-open to open, then you open new ways. The other is that it's for a fixed shape, for a fixed shape, it's a polynomial in P. Why? Because probability of every configuration is polynomial in P, so it's just to count how many blue, take P to this power, how many yellow, 1 minus P to this power, multiply, so that will give you probability of this configuration, then you add up. So it's for every given shape, it's a fixed function, and then the question is sort of so fix shape, send lattice mesh to 0. So you basically what you do, you fix some shape, and first you do one lattice mesh, or I drew square lattice because it's easier. Then you use a much smaller one, and you always get a polynomial function which is increasing, but the degree of the polynomial will be bigger and bigger, so they can approximate basically whatever you wish. So the theorem, the first theorem is that there is a value PC, shape independent, such that the limit of this PP as delta goes to 0 is equal to 1 when P bigger than PC, 0 when P smaller than PC. And so basically what happens is that there is some number PC. So our probability, obviously it is increasing. Also, actually, I should say that at number 0, probability is 0. At number 1, probability is 1, because then it's everything close to everything is open. So what happens is that if you successfully do small and small meshes, then you get graphs which are closer and closer and closer to a graph which is constant 0 up to this point, constant 0, constant 1 afterwards, and has some non-trivial value in between. So this is what you would physically expect. So this is, for example, if you have like a city and you want to drive through, and there are roadworks at every intersection with some probability P. When you increase P with small p, you can still drive through. For large P, it's completely closed, but this change, it just happens at one value PC. So PC is lattice dependent. So PC is lattice dependent. PC for hex lattice, for hex, PC is equal to 1/2. So what I said up to now is a theorem which is a combination of a theorem of several people. So there are 3 people, Russo, Seymour, and Welsh, who first did the required estimates. Then Harry Keston, he proved that PC is equal to 1/2. And then Eisenman and Barsky and Menshikov, they sort of figured out these things which are called sharp threshold. So I will give a short proof of this theorem. It's sort of a very much digested and redone original proof, which is now condensed to less than 10 pages. So the original was very complicated, but it had also some corollaries which I'm not doing today. Well, at the time it was a really big achievement, because while you expect this sort of sharp threshold in many physical systems, that along with the Ising model, it was physically established earlier, but mathematical proof came later, and percolation maybe was the first real physical model where it was shown. So first I will do something which is called an RSV, Russo Seymour Welsh estimate. So given a shape, there exists constant C, so it's constant of this shape, so that the probability for P equal 1/2 of the crossing is smaller than 1 minus C and bigger than C. So if I fix a shape, so for example, I can fix a shape which is very, very, very long. So if a shape is very, very, very long, there is a very low probability that there is a crossing because it has to go all the way through. But still there will be a given, there will be some constant, very small, such that no matter which mesh I put, I will have probability that of this crossing bigger than C. And this is sort of kind of indicates that PC should be equal to 1/2, because you have some non-trivial estimate, and if we believe in this picture, PC should be 1/2. So this is an indication that PC is equal to 1/2, not a proof yet. So the proof has 2 parts. So the first part is that for a symmetric shape, P 1/2 of the crossing is equal to 1/2. Now, what do I mean symmetric shape? Well, symmetric shape, by symmetric shape I mean a shape so that there is a symmetry which kind of flips it over. So on square lattice, square is symmetric. On hexagonal lattice, well, it's better take not a square, but for example a rhombi with the angle 60 degrees and the same length of sides. Then for triangular lattice it is symmetric. Or you can take a square but rotated by 15 degrees. So you need a shape which is symmetric. So why this is true? So let's first look what is the probability at a number P to have a vertical crossing in blue. So this is exactly 1 minus probability at P to have a yellow abstraction. So this is a property of this particular graph being trivalent. So if there is a blue crossing, there is no yellow abstraction. You cannot draw a yellow thing. On the other hand, if no blue crossing, then you sip, you have to stop, and then there should be some yellow thing which prevents you. So it's a property of hexagonal lattice. That's not true on a square lattice, because on square lattice you can have a chessboard covering where half of the squares are yellow, half are blue, and you don't have a crossing. It's really a property that in every vertex you have 3 hexagons. So what you do to prove it, you just pour blue from top to the bottom. If it reaches bottom, there is a blue crossing. If it didn't reach the bottom, it means that you go on the boundary which it reached, and then you find a yellow abstraction. So either there is a blue crossing or there is a yellow abstraction. So there is the interesting story about it. There is a game, we used to have it in our room, which is called Game of Hex, where 2 persons put yellow and blue hexagons on the board in turns, and the first person wins if he has a blue crossing up-down, and the second wins if he has a yellow crossing left-right. And this observation just says that this game is well defined. At the end, exactly one person will win, either the first one or the second. So it was invented by some Danish guy, Peter Haig, and independently reinvented by John Nash, the famous Nobel laureate. So in the common room on Princeton Math Department, they still have the game of hex he made out of cardboard. So it's a very simple and interesting observation. So for all models where this observation is true, you can prove that PC is equal 1/2. For models where you cannot use this observation, there are possibilities that PC is some other value. For example, for triangular lattice for bonds, PC is twice sine pi over 8 or something like that, and that you can do reducing it to this lattice by some transformations. Or for square lattice, as I said, there PC is supposed to be some transcendental number like 0.58 something. People calculate, I think, 10 digits after the decimal point. It doesn't look rational, so it's not something specific. So okay, so we have this property, and that we can write. So this is the same as 1 minus, so if you switch the covers to the negative, so the probability of having a closed crossing for P is the same as probability of having open crossing for parameter 1 minus P, because here the yellow cover has probability 1 minus P, and the blue cover has probability P, so this is, okay. So when we do to the negative, we go to the negative, we should exchange blue and yellow. And if you have a symmetric shape, then you can flip it over. You get 1 minus P, 1 minus P, the vertical crossing. So if P is equal to 1/2, we get that P 1/2 of a crossing is equal to 1 minus P 1/2. If P is 1/2, these two indices are the same, the crossing. So you get that probability of a crossing is equal to 1/2. Now, the second part is you have to pass from a symmetric shape to an arbitrary shape. So from symmetric shape so it's very easy to do once you already have some elongated shape. So that's what first Russo, Seymour, Welsh have noticed, is that if you already can do, for example, shape 1/2, then you can do shape 1/10 just by sort of snaking through. So you do snake like that, and if each of the dominoes has a crossing, from their crossings you can construct the global one. You should be a bit careful. You should prove that they have positive correlation, this crossing. So the fact that you have this crossing only increases the chances of that one, but that's fairly easy for percolation. So so it's easy, for example, to show that probability of crossing something like shape which is, let's say, A times NA is at least probability of crossing the shape, let's say, A over 2 times A. And how many times you should snake it? So you should basically do, you should cover it by the shapes of length A, basically n times like that, n times like this, and twice n, something like 4n. Well, 4n minus something. So this is very easy to see. So, but the question is, how do you get shape 1 by 2, get something elongated? And that's where Russo Seymour Welsh came up with the trick. So I want to do a simpler version of this trick. Suppose that we take any rectangle. Any rectangle, let's say R. Then what I want to show is that the probability at 1/2 of crossing twice this rectangle, so it's this rectangle but double, so is at least probability of crossing this rectangle squared over 16. It's a very poor estimate. In fact, one can do better. But then already you can stack them as you wish. You can snake them using this, and from that everything follows. Okay. So this is just a sequence of pictures. So we are on hexagonal lattice. So there are three symmetries. You can mirror with respect to 3 directions. There are 3 directions in hexagonal lattice. We'll use only one direction, the vertical one. So what we first say that probability at 1/2 of, so I take this double rectangle of crossing the left part is, let's say, denoted by A. Now, what I do, I take the lowest possible crossing. So I push it down as much as I can, and if it's the lowest possible, it actually means that there is a yellow obstruction on the bottom so that I can't push past it, but I don't use it. So I take the lowest one. So the lowest one, so we take the lowest crossing, let's say gamma. So the important observation is that the lowest gamma depends only on the area below. So it only depends on this area. So because if I know this crossing and I know that below there is no other crossing, if I change something above or on the right, nothing will change. It still will be the lowest crossing. And this allows me to resample the area above and the triangle on the right. So the important point is that we can resample the rest. So we can play with the rest as we wish. So what I do, I take the symmetric, gamma prime, the symmetric curve. So symmetric let me draw it like that. So the symmetric which goes like this. And then I have this butterfly shape. And in this butterfly shape, I can study two crossings from gamma to the opposite side and from gamma prime to the opposite side. So since the shape is symmetric, probability of this crossing from gamma to the opposite side will be exactly 1/2, the same trick. So I get that probability at 1/2 of having a crossing which goes like this. So I have this one and then I go from it either here or here, is equal to A/2. And what can happen with this crossing? Either it lands above or it lands on the right. So there are two possibilities. So so it follows that either the probability, either we landed on the right or we landed above. So since the sum is A/2, at least one of them will be at least half of that. So this is at least A/4, or this is at least A/4. So the first one we already done, because it means that the probability is at least A/4, so it's at least A²/16, so we are done. So we're constructing our crossing from left to right. So the bad thing is that if we didn't reach it, if we landed on top. And it turns out that this also can be worked through. So we just need one more trick. So suppose that probability at 1/2. So the second case, probability at 1/2. So we cross from the left side to this top. So this probability is at least A/4. So you remember we started with this trick that we take the lowest crossing. Now we take the leftmost uppermost crossing. So choose the leftmost uppermost crossing. So it only depends. So only depends on the sector above. So we resample the rest. So we can resample the rest of the picture. And by symmetry, the probability at 1/2 that in the rest of the picture you have a symmetric version of it, so you have some symmetric version which goes like that, is at least A/4. And then what we do, we combine them, and we get that probability of having this crossing, and then the part of the other one is at least A²/16, so we are done. So what we used over and over again is that percolation doesn't care about the boundary conditions, so we can move the crossing, and when we have this shaded part, but the rest we can resample. And the second thing we used is that there is this geometry involved. So for the Ising model, when you study correlations of the spins, you cannot quite use the geometry. And since then, such methods, they were applied to other models like Ising model. So there is a way to rewrite Ising model as a percolation type model. It's called random cluster model or Fortuyn-Castellane model. So there is a version of the Ising model where in the new version, probability of being connected corresponds to spin correlations in the old one. But unfortunately, it's unlike percolation, it has boundary conditions now, so it's slightly more difficult to play these games, but still people do play these games also for a version of the Ising model. Okay, so what we have shown that the point 1/2 is special. So how do we show that there is this picture? So I have 10 minutes, so let me show it. So I want to show that. So it's the sharp threshold. So first, there is a so-called. So we want to look at this event, and that there is a thing which is called Russo from Seymour, Welsh, and Margulis, well, the famous Margulis lemma, which says that the derivative in P of probability of some event is equal to expectation, this value of P, of the number of hexagons of pivotal hexagons. So here the remark is that the V is pivotal for event X if for configuration omega for event X, if omega with V yellow, omega with V yellow gives you X, and omega with V blue, so it's open and closed, gives you not X. I think the easiest one is to look at the crossing. If X is a crossing event, what does it mean that some hexagon is pivotal? It means that when it is blue, there is a crossing, and when it is yellow, there is no crossing. So it means that if there is a crossing, it has to go through it. But on the other hand, if we switch it to yellow, then there must be an abstraction. So there has to be abstraction which goes through it. So this is pivotal site for crossing event. So its pivotal is equal to this sort of 4 arms event. So basically, it's if you think about driving through a city, what does it mean that some square is a pivotal? That when police closes it, you can't pass through. When it opens it, you can pass through. It means that there is only, there might be several ways to pass through, but each of them leads through this square, and if it's closed, then there is this barrier across the city. And this, again, is some geometric thing with which one can play, because look, here we played with one crossing, here you play with 2 crossings intersecting at a point. Now I said that number of pivotal hexagons because there might be several pivotal things. For example, it can happen that, well, let's say, look at this picture. In this picture, there are 2 pivotal hexagons. Each of them, when I flip, I get a crossing event. Now, why Russo-Margulis lemma is true? Well, it's sort of trivial. So what happens if you increase P continuously? If you increase P continuously, you just flip hexagons one by one. And then when the event changes, when you flip one of them and change, so when one of them is pivotal. So maybe let's do it as an exercise. So it's an exercise on coupling, which is one of the important things in probability. So you should couple configurations for different values of p. I already said how to couple p and p plus epsilon. So here the easiest one is that to look at the following model, that you toss a coin at every hexagon, which gives, it's a special coin, gives you a real number between 0 and 1. So at every hexagon you write a 0, 1 uniform random number. And then you choose the value of p, and the hexagons which have smaller number than p, they are open, and the bigger number, they are closed. And then when you just raise p, they flip one by one. So actually the contents of this lemma is that when you raise the value of p, it's 0 probability that you flip two hexagons at the same time. But it's 0 probability that two independent real numbers are the same. So this is Russa-Margulis lemma. So Russa did it in the context of this planar percolation, Margulis for something else on calligraphs of groups, slightly different thing. So what I want to show, so sharp threshold. So derivative in p, probability p of the crossing event, it's equal to the expected number of pivotals. And I will write an estimate from below on this number. First, you know, for simplicity, yeah, I know, maybe no simplicity. So it's what do you have to have a pivotal? Well, to have a pivotal, you first need to have a left-right abstraction. So left-right abstraction, it has probability 1 minus the probability of a crossing. So this gives you probability 1 minus probability of a crossing. So it's 1 minus probability p of crossing. Now choose the lowest. So I choose the lowest, so I push it as far down as I can. If I can't push the abstraction further, it means that on the bottom it's touched everywhere by blue clusters. Now what is the other thing I have to have a pivotal? I have to have the blue touching above. And the probability of this is the probability of blue in this smaller rectangle, which is at least probability of the blue in the big rectangle. So at least probability of a crossing, because it's much easier to cross halfway. So it's at least probability p of crossing. So this is not this is an estimate from below, because this is an estimate of the event that we just have one crossing. So just one pivotal. Again, here I choose it the leftmost. So we again choose it leftmost. And now you do the following thing. Look, this is your pivotal point. But for example, if there is a crossing like that or like this, you get another pivotal point. And what you do, you take this point and you take concentric annuli around it of the same modulus. Well, if you prefer, you can do them on the lattice. So suppose that the size of the box is n. So let's say n size of the box. How many concentric annuli from size 1 to size n? if you do concentric, each is twice bigger than the previous one, how many of them can you fit? Logarithm n. So you can do log n, constant log n concentric annuli. And in each of them, by Russo-Seymour-Welsh, there is a positive chance of finding a crossing. So by Russo-Seymour-Welsh, each probability at least some constant of crossing. So that's, you can apply Russo-Seymour-Welsh when p is bigger than 1/2. So it's, so p bigger than 1/2, because we did Russo-Seymour-Welsh for p equal 1/2. So we get this formula, this times constant log n. So I get the following equation for my function. F prime is at least f times 1 minus f times constant log n. Which means what? Which means that if my function is close to 0, this estimate is useless. If my function is close to 1, it's useless. But when f is not 1, not 0, f times 1 minus f will be some definite number. So when it's not 1, not 0, I get estimate f prime is at least logarithm n. So for box of size log n, derivative of a function in this central part will be at least logarithm n. So we basically, that means, well, I have erased people who proved this theorem. So this means that the graph of our function is inside a strip of width constant logarithm n, constant 1 over log n. So it means that our function lives inside this snake of its constant logarithm n. So, and the bigger the size, the better sharp threshold we get. So a small remark is that I did a very straightforward thing with annuli, but what I can do the first crossing and then start the annuli again. So actually what will happen, there will be a counter set of these points, so the one can actually do f prime is at least constant f1 minus f times 1 or times n to the power epsilon. So that was actually easy to do by just sort of looking at the fractal structure of this set when it's how often they go. And in reality, it's actually even better. In reality, we know, so this is easy. And after SLE, one can do that f prime is at least constant f times 1 minus f times n to the power 5 quarters. So it's indeed, so what this means, for example, that suppose that I take a box of size 100 by 100. Then it means that essential derivative of my function when it's not close to 0 or 1 is at least 100. So it's already in a box 100 by 100, it is very, very steep. So if you run computer experiments for a box 100 by 100, essentially you would see function which is, well, for 100 maybe not, but for 500 by 500, essentially we see constant 0 and then constant 1. So it converges very, very fast. Okay. Okay, so what did we prove? So we did, by the way, we did this for p bigger than 1/2, and for p smaller than 1/2, you should just revert to the other event, to the abstraction event. So this we did for p smaller than 1/2, go to the negative, get p bigger than 1/2. So the proof also works. Okay, so what we proved in the first half, we proved that PC is equal to 1/2 for hexagonal percolation, that there is this sharp threshold phenomenon, and also we did some estimates, which Russo-Seymour-Welsh, which will tell us that the observables I'm going to write, they are Hölder continuous functions. Okay, so let's have a break. We'll do this self-dual percolation where P is equal to 1/2. And what we'll actually do, we'll calculate the probability of crossing a given shape. And as you remember, for SLE we calculated the same probability. So we'll see that it corresponds to that of SLE6, so one can deduce convergence to SLE6. So before the work of Schramm, there was a calculation by John Cardy, who is a physicist, so it was a kind of a physical calculation. So what Cardy did, he fixed the 3 corners and he moved the 4th corner and looked how probability of crossing behaves. So I want to first, I want to move this point inside the domain, but first I want to rephrase this model. So it's let's say percolation is equal to what is called, well, a loop model. More specifically, it's what is called O1 loop model. So first, a very sort of a simple observation. So suppose I have some domain okay, let me just draw a little bit bigger piece. And suppose I have a percolation picture here. So it's something like that. Then the important things, well, you can do the blue crossings, or you can draw the interfaces between blue and yellow. So you have a picture like that. And what you can do, you can forget about the colors. So you can do this picture, the very same picture, but you forget about the colors, you just draw these interfaces or domain walls as they're often called in physics. So you will get, in this particular case, this picture. So what is important is that there is basically a bijection between these two pictures. So if I fix, for example, if I fix the color of, let's say, some hexagon, then I can just start coloring, changing the color whenever I cross an interface, and there is a unique way to color the picture. So basically that, so there is a bijection between colorings of omega and loop configurations. And to have a bijection, you need to fix a color of one hexagon, so fix color of a corner. In particular, that means already some interesting thing, because it means that the partition function of percolation is equal to partition function of this loop model. But partition function of percolation is just 2 to the power number of hexagons. Because each hexagon can be covered two ways. So partition function of loop model is the same, 2 to the power number of hexagons. Now suppose I want to study the crossing events. So we just proved that the possible number of loop configurations is exactly 2 to the power area, which is not immediate. One has to think. There is one subtle point I did not touch. What are the boundary conditions? So I just said that there is one hexagon which is blue. So let's do the boundary conditions, all blue below, all blue above, and yellow in between. So I'll do boundary conditions like this. So we have a domain with 4 boundary points, let's say A, B, C, and Z. Do boundary conditions which are blue on the arc BC, blue on the arc AZ, blue and yellow on the arc AB and ZC. So what kind of loops we get in this case? So I need to slightly change. So there is this loop as it was. There is this loop which goes like that, and then it ends up here, and it ends up here, and it ends up here. So the boundary condition for loops becomes that there are 4 sources at 4 different points. So this is the boundary condition for the loop model. So it goes like that. And there is another interesting observation that if you have a vertical blue crossing, then it forces the loops to be connected A to B and C to Z. On the other hand, if you have yellow horizontal crossing, it forces the loops to be connected the other way around. So there are, if you have 4 points on the boundary, there are 2 topological ways to connect them because they cannot crisscross. So it means that the crossing probability has a perfect meaning in the new model. It's just the probability of these things connected in that way. Okay. So now what Cardi was doing, he was moving this point and looking at how this probability changed, but in purely physical terms. So he used some physics intuition to sort of tell that the derivative of this probability is connected to its own square, and then he got Riccati equation, and its solution was a hypergeometric function. What we do instead, we allow the point to move inside. So we allow the point to move inside, so we look at the following picture. So it's, let's say, A, B, C, and Z. And Z. So in the first model, well, what was the crossing event? It was separating 2 points from the other 2 points. So it was, let's just do the same crossing event, that there is a crossing which separates these 2. And now the question is, what does it correspond in the loop model? Well, there is a tricky thing about loop model. If you just say that there is a loop which, well, let's say, which ends at Z, this configuration, well, there will be many more small loops. So this configuration doesn't admit a canonical coloring blue-yellow, because when you go around this point, you cross once the interface, so blue becomes yellow. So this is what physicists would call a disorder operator. So for example, if you do it for the Ising model, there is sort of canonical relation that its kind of like a spin in the dual-Ising model, if you take appropriate weights. So if I take these two definitions and allow Z inside, in one definition I get this picture, in another I get that picture, and there is no immediate bijection between them. But it turns out it's a lemma which one can prove. So the lemma is that the number of these pictures is equal to number of that pictures. So there is a sort of bijection between them, in a sense.
What are boundary conditions?
Here there are no boundary conditions for percolation. They are not important. You just ask that there is a crossing between these two arcs. If you want to go here, then of course the boundary conditions would be that you start with blue, then the next arc has to be yellow, then the next arc has to be blue, and then oops, it has to be yellow. So it's kind of well, contradiction. You cannot do covering. So for percolation, you see, for percolation, it's not really important. If you do Ising model, then it becomes kind of, you have plus boundary conditions here, minus boundary conditions here, plus again, minus again, oops. So unless you have criticality, where, well, so it's sort of kind of shows that the loop model is better. You can do more things with it than with the covering model. I'm not sure I want to prove this lemma, but I will just give you an idea of the proof. So what you do, you take the leftmost possible crossing. So you take the leftmost possible crossing. So it depends only on the area below. And we know that Z is above. Now we fix this gamma. Now suppose that this area is omega gamma, that the number of configurations is equal to 2 to the power area of omega gamma. Now we do the similar picture here. So I fix the area which is to the left of this guy. Well, strictly speaking, you probably need, if this guy has a fjord, you need also to include it. Now we have this omega gamma, and what happens with omega gamma? I want to count how many configurations I have where this interface ends in the middle. And I claim that it's again 2 to the power area. Why? Because what do you have to do to end the interface in the middle? You can do the covering, but you do one crosscut, and when you cross this crosscut, yellow becomes blue. So whenever you have a yellow hexagon, the other half of it's blue, and whenever you have a blue hexagon, the other half of it's yellow. So we do one crosscut which has this funny property. Then when you cross this is a specific line. When you cross it, yellow becomes blue, blue becomes yellow. And then what this will force? It will force that there is one interface which ends at this point. Well, I can draw a small neighborhood of this point, how it will look like. So let this be this point, and let this be its crosscut. So if I cover this in yellow, this in yellow, this in yellow, then this half has to be blue. So this is how this thing will enter. So if I do this crosscut, I see by the very same logic that the number of loop configurations is exactly 2 to the power area. But only now the loops are. And that is true conditioned on gamma, and then you average over all gamma and you get the thing. So there is a corollary. The corollary is that if we do okay, I'll do corollary in a second. It's better to do it. Ouch. It's better. So let's define three functions. Well, maybe I denote the points not A, B, C, but 0, 1, 2. It's easier like that. And I define the functions H0 is the probability that H0 of Z is the probability that Z is in one component with 0 and another component is 1, 2. And this is 1 over 2 to the power area. Well, the number of configurations where you have this picture. But then you have similar functions H1 of Z and H2 of Z. So they give you three different pictures. Wait a second, I want to do it counterclockwise. So it's 1, 0, 2. So it's well, on the right, I also can write probabilities in principle because we have shown that this sums to 1. Now, the first observations, well, there are two observations which are corollaries of this. The first corollary is that functions Hj and they're Hölder. Uniformly Hölder, because Hj of A, well, Hj of Z minus Hj of U is no more than, so if you have 2 points U and Z, what does it mean that one of them is separated by a crossing and another is not? It means that there is a crossing which goes in between. And by Russe-Seymour-Welsh, it means that there is a crossing of an annulus. So it's by Russe-Seymour-Welsh, you get that the probability is less than probability of a crossing the annulus. So it will be U minus, there will be constant U minus Z to the power, some small power epsilon. Which is already a very nice statement. Why U minus Z to the power epsilon is just we do the same thing with sort of telescoping annuli. So if you have annulus of the modulus U minus Z, then you can fit log U minus Z annuli inside, and each of them, so it's, yeah, maybe I do by Russe-Seymour no more than probability of a crossing annulus of R to twice R to the power logarithm of U minus Z. Which is no more than by Russe-Seymour-Welsh than, like, say, 1 minus epsilon to the power logarithm U minus Z. which is no more than u minus z to the power logarithm, well, whatever. So this is how you get an estimate. So that means that we can assume that as mesh goes to 0, hj converges to functions hj small uniformly, because so this is true for subsequence. So we choose subsequence where they converge uniformly because Hölder continuous functions, they are precompact in any reasonable space, like continuous functions. And then we work with the subsequential limit, and then we'll see that we can determine it, so we can determine it as a limit. So that's the first thing. The second corollary is that sum of hj of z is identically equal to 1. And the proof is quite easy, so it's very interesting that you don't see it immediately for these pictures, why these three probabilities should sum up to 1. But you see it for these pictures, because for these pictures it's the number, so this sum of hj of z is 1 over 2 to the power area, number of the pictures where you have 4 sources in the middle and 3 on the boundary. Because well, you add this picture, this, and this, and this. So this is sums all 3 possible ways to connect them. But the number of such pictures is the same as number of coverings. Just this crosscut trick tells you. So it's 2 to the power area, the number of coverings over 2 to the power area, so it's equal to 1. So whenever I do covering with a crosscut, I force some interface to start from this point, and then there are only 3 possible places where it lands. If it lands in place 0, I get h0. In 1, h1, h2, because 2 other sources they have to connect. So this is very nice. We found an analytic function in our model, but the analytic function is identically 1, so it's not very helpful. It doesn't prove anything. It's a nice observation, and actually I'm not sure well what it signifies for these probabilities. But we want to go more, so we want to do some other thing, and preferably symmetric. So we define function f of z to be sum of, let's say, tau to the power j, hj of z, where tau is the complex cube root of unity. So it's basically h0 plus tau h1 plus tau squared h2. So it's the next symmetric thing we can come up with besides their sum. So the thing which I want to say is the following lemma. So suppose we have some vertex. So our function is defined on edges, as I said. So h we define, so z is an edge. Why I define it on edges and not on vertices? Because if I define it on edge and I do this sort of cross-cut trick, there will be one interface leaving this point. But if I define it at a vertex, in principle it can happen that there is one interface leaving it, but also there might be a picture where there are 3 of them leaving in 3 directions. And that I don't like. It will then create some problems. So that's why we don't do it at vertex. So the lemma is that if we take some vertex v, so there are 3 nearby points. Well, it can be this vertex or reflected vertex, but let's say this one, and let me denote them P, Q, and R. So what I claim is that f of p plus tau f of q plus tau squared f of r is identically equal to 0. So this is, immediately before I prove it, it's Cauchy-Riemann equation, which I have written here. Because if I try to do a discrete contour integral, suppose that I want to do a discrete contour integral along, or contour sum along this contour. So the contour sum around this triangle, around triangle T, will be f of p times this edge and its length, let's say delta, plus this is I rotated by tau times delta f of q, plus I rotated by tau squared delta f of r. So this is I delta times this thing, f of p plus f of q tau plus f of r tau squared, so it's 0. So it's basically, this is like Cauchy-Riemann equation. It says that the contour integral of my function around a contour is 0. So sticking this together, so if we take a bigger portion of a hexagonal lattice, and we add these contours together, so I do these contour sums over all the triangles. So if I contour sum over all triangles inside some contour, the edges inside will cancel out, so I'll get a contour sum along the boundary. So take a big contour gamma, then the 0 is the sum of this Cauchy-Riemann for T, where T is a triangle inside gamma, and this is just the contour sum around gamma of f of z dz. And we assume that there is a subsequential limit, so hj converges to hj, then f converges to f, and then it means that the contour integral of f dz is equal to 0, so it means that f is holomorphic. So any subsequential limit is holomorphic. So I want to make here a small remark that this is very different from loop erased random walk and uniform spanning tree. It looks the same, but it's a bit different. Well, very different. Because in uniform spanning tree, we had genuine Cauchy-Riemann equations, and we didn't even, in principle, we didn't have to use any properties of uniform spanning tree. So what we have here is not exactly Cauchy-Riemann equations, it's 1/2 of them. We say that for every placket, the sum around it is 0. It's like, for example, saying that the current is curl-free, that there is no curl around this placket. So if you want to have a real Cauchy-Riemann, you need also to show that, for example, around every hexagon the sum is 0, which we cannot do. We only have 1/2 of it. But unlike UST, we know much more about percolation. We know that f has a limit, which is an analytic function. So we know that, basically, we know that the limit of f is independent of the direction of the of the interval. So for horizontal intervals, so intervals at 60 degrees, the limit will be the same because limit of functions hj will be the same. And sort of indirectly, we get another Cauchy Riemann, the other half of the Cauchy Riemann from this one by sort of plugging in edges in different directions. So it's kind of a sort of peculiar thing. So what I want to emphasize that just this equation alone, it does not determine the function f uniquely. Because this equation alone is like a flow of liquid being curl-free, or flow of liquid being divergence, well, more divergence-free. So if it's a flow, the divergence at this point is 0. There are many divergent-free flows on a graph. But in the limit, it becomes this because we know that our flow is independent on the direction, that our flow in the limit is independent on the direction, and then it becomes genuine Cauchy Riemann in the limit. So it's kind of here Cauchy Riemann is generated, so it's just a word of caution that it's not, it looks like Cauchy Riemann, but in discrete setting it does not give us a discrete analytic function. It gives only half of discrete analyticity, but the fact that the function has the same limit on different edges allows us to deduce that it's holomorphic. Okay, the function is holomorphic. Now what do we have to do? Well, we have still to prove this equation, and we need to figure out the boundary conditions to figure out what kind of function that is. Let me first figure out this equation. So I want to do the equation. Let me do it again. P, Q, R, and I want that f of P plus tau f of Q plus tau squared f of R is equal to 0. And I want to recall that f is h0 plus tau h1 plus tau squared h2. Now let's have a look at what kind of possible contributions we have to this picture. Well, there are different kind of contributions. So for example, what we can have that well, say from point 0 we arrive at this edge and there is nothing here, or and then what we do, we yeah, let me draw so there are essentially three different situations. So one different situation that we arrived here, there is nothing 0 here, and then what we can do, we can extend this one step, or we can extend it one step in the other direction, and we get a picture which contributes to Fp or Fq. So it's very, very easy. So what happens that this picture contributes to this one, this picture contributes to this one with coefficient tau, this contributes to this one with coefficient tau squared, and they all three are h0. They all three are h0, so this is h0, h0, h0. So basically the contributions are 1 plus tau times 1 plus tau squared times 1, which are 3 cube roots of unity, so it sums to 0. You can ask what happens if we arrive here and there is already a cycle. Well, nothing much. You can do sort of a train track change and you get again exactly the same contribution. So again it's h0, h0, h0. So if it were just these three pictures, we would get that h0 is satisfying this equation. But there is a more complicated picture that we arrive at this point, and here there is a connection between points 1 and 2. So we have a picture like that. So we can do the same train track game, so we can change train tracks here, but what we get is that these three contributions would be to h0, h1 and h2. So the first one will contribute 1. The second one, there is coefficient tau in front of f, but since it's h1, h1 comes with coefficient tau of its own, so it's times tau. And then the third one is tau squared, and again h2 comes with the coefficient tau squared, so it's tau squared. So it's 1 plus tau squared plus tau to the power 4, again 0. So it's a sort of a easy combinatorial argument. So once again, it sort of says for a complex function that at every point, sum of its values around it on edges is 0. So it's like the field being divergence free. But then, since we know that our field has the same limit on edges of all directions, it actually translates to the genuine Cauchy-Riemann. Okay. So what I concluded so far, that the function f has a scaling limit subsequential, and it's holomorphic. Now we need to find the boundary conditions. So let's say the boundary conditions. So we have our domain 0, 1, 2. So f, once again, it's equal to h0 plus tau h1 plus tau squared h2. So, and h0 plus h1 plus h2 is equal to 1. So it means that f is a convex sum of numbers 1 tau squared. So f is convex sum of numbers 1 tau squared. So convex sum is sum with coefficient summing up to 1. So it means that f automatically will be inside the triangle with vertices 1 tau squared. So f automatically will take the values inside this triangle. So it's just an equilateral triangle on 3 cube roots of unity. But what happens for z on the arc 0, 1? What are the possibilities? Well, there is obviously h0, h1, h2. So for h0, you need a picture like that. Well, it can happen. For h1, you need a picture like that. For h2, you need a picture like this. But then, well, our arcs will crisscross, and that is not possible. So this is bad. So on the arc A01, f is a convex sum of with coefficients h0 and h1. Convex sum of numbers 1 and tau. So you get a number on this interval. So the image of this arc is exactly this interval. So in the limit f of arc 0, 1 is exactly the interval from 1 to tau. And f of arc 1, 2 is exactly the interval from tau to tau squared. And f on the arc to 0 is exactly the interval from tau squared to 1. So what you get is that f is a holomorphic function which takes the values in this triangle and which maps the 3 boundary arcs exactly to 3 sides. So it means that f is a conformal map. So it means that f is a conformal map, rather the conformal map to this triangle. So omega to the equilateral triangle. In particular, it means that the crossing, so if you want to calculate the crossing probability, so when you take z on the boundary, you have to map to an equilateral triangle the 3 vertices, and the third vertex will be mapped on the boundary, and if the u is the length of this interval, then the probability will be exactly given by this length. So probability of a crossing an equilateral triangle will change linearly just as the function h changes linearly on the boundary. So these three functions are basically the three coordinates, real coordinate at the angle 120 and coordinate at the angle 240. So they are three linear functions, and just for this proof it looks easier not in the usual coordinate system at 90 degrees, real imaginary path, but in these barycentric coordinates where you take basis vectors 1, tau, and tau squared. Okay. So we proved that any subsequential limit of function f is holomorphic with this boundary value, so it is exactly this. So means we proved that there is a scaling limit which is exactly that, and that tells us that so the corollary, so the probability at 1/2 of a crossing omega, so there is a limit as mesh goes to 0 of this probability. This limit is conformally invariant. And then if you want a formula, there are two ways, well, there are many ways to get a formula, but two ways that in probability in an equilateral triangle of size 1 to cross between size 1 and, well, let's say, interval of length x, it tends exactly to x. So this is now this formula was observed by Leonard Carlson, but the original formula for Hardy, so he wrote a differential equation and he showed hypergeometric function as a solution. So it's so Hardy uniformized it to a half plane, and then the crossing is let's say let me just see so that I don't. Well, we actually written it up for SLE, so it's the same formula. So I always mess it up whether I did it for m or 1 minus m. So for this probability, that will be just a second. So integral from 0 to m times 1 minus m to the power minus 2/3 over the same integral from 0 to 1. Now for m equals 0, I get 0. Yeah, so it's this one, from this arc to this arc. And this is also what is called hypergeometric function. So it's denoted 2f1, 1/3, 2/3, 4/3. So these are the powers in which you have the monomials at a point m. And then we normalize it, and the normalization is can be written either as this function at point 1 or as gamma functions, which are gamma 2/3 over gamma 1/3, gamma 4/3, and m to the power 1/3. So that's the formula. So it's not, in a sense, it's not a scary formula. It's just the notation for this ratio of integrals. Another way is to write an infinite series. Another way is to write some equation. Now, maybe, let's say, an exercise. Show that these two things are the same. Oops, it doesn't write. Exercise, compare these two things. Basically, exercise is to show that integral from 0 to m m times 1 minus m to the power minus 2/3 maps triangle, well, it should be m to the power 1/3, so that this formula maps, so this integral maps half plane to an equilateral triangle. And points which are mapped to the vertices are 0, 0, 1, and infinity. So these are points where exactly there are. So the hint how you do it, you don't work with function f, but you work with its derivative. And what should derivative do? It should rotate these different intervals by angles 0, 120, and 240. So that's where the powers kick in. Okay. Now, I don't deduce from this converges to SLE6 because this is just the same thing as we did. You take this formula, you plug it into SLE, and you deduce from it after many steps that, after many calculations, that expectation of AT is 0 and expectation of AT squared is 6t. So this is what you deduce. Again, it's specific form of this formula. Is there anything special about it? Not really. If you do this for other SLEs, for other models, there will be similar hypergeometric function, but with different numbers, so there will be no hexagonal, no triangle, but some other things. If for some other models you can prove this formula, then you can show relation to SLE and deduce many more things. So here, it was originally supposed that hexagonal lattice should have something to do because in the answer there is a equilateral triangle. Well, it helps, but it's not hexagonal lattice specific. If you do percolation square lattice, you are supposed to have exactly the same formula. Only we cannot do it because we don't know combinatorial magic similar to this one. So the big problem, for example, do the same thing on square lattice. Now, this may not seem like a growth process, a genuine one. It's, of course, growing this interface. But it has been related to the growth of processes like water seeping through medium or fire burning through the forest, because essentially the boundary of this blue cluster, the water seeping through, is described by SLE, and it indeed appears like a growth process. Only we give it not as a boundary of process like water seeping through, but rather as a walker which goes around the perimeter which already seeped through. For which models SLE convergence is known? It's known for loop-raised random walk and uniform spanning tree. It's known for percolation, but only on this lattice. And it's known for the critical easing model on basically any reasonable lattice. So there is the combinatorial trick is richer. But then there is a whole spectrum of models where it's wide open, and so far all the proofs they use some combinatorial magic. Okay, so I think that's it for the model. So what is, maybe I did not say, but now it allows you to relate to SLE, but then SLE, for example, allows to calculate dimensions. So for SLE, it's SLE6, so we get that the dimension of these red curves is 1 plus kappa over 8, which is 1 plus 6 over 8, which is 7/4. So the perimeter of percolation cluster, if you go into all the fjords, is 7/4. If you don't go into fjords, it's 4/3, so it's smaller. It's again another SLE. And you can basically, for percolation, now in hexagonal lattice, we can calculate everything just by plugging in SLE. At least we can do all the previous conjectures. Okay, so that's it for today. Next 2 times we'll do Hastings-Leavitt, and then before Christmas we'll do DLA. That's the plan. Okay, thanks.